After you collect data, specifically numerical data, you want to be able to summarize the data by describing some important characteristics that you notice about your data set. So anytime you use specific values to summarize your data, we call this descriptive statistics. So descriptive statistics are just values that summarize or describe important characteristics about your data. So we're going to focus on looking at different types of statistics that summarize or describe. Specifically, we'll look at measures of center, and then we'll look at measures of variation and measures of relative standing. So what are some different measures of center? Measures of center include values such as, let me get my pen here, values such as your sample mean, your median, mode, and mid-range. So let's remind ourselves of what a mean is. And if we're talking about a sample mean, then I'm referring to X bar. So to calculate the mean for your data, what you want to do is you want to take all the values in your data set, so all your values, and you want to sum them up. So that's the Greek symbol for sum. And then you divide it by your sample size, okay? And that gives you your sample mean. Now, if you want to calculate, and also most of you probably think of the sample mean as the average, but it also is used to describes the typical value of a data set. Okay. Now, the median is when you take your data and you order it from least to greatest. So you order data from least to greatest, right? The median is the middle value. In the center, you think of that as the middle of the data set. Okay. When we talk about mode, mode is the value that occurs the most. And then the mid-range is the value that's midway between your maximum number and your minimum number in your data set. So if you want to calculate your mid-range is just take your minimum value, add your maximum value, and then divide that by 2. That's going to give you the mid-range, okay? Let's take a look at an example of some numerical data and its distribution. So below on the left here, I have a histogram for the weights of 147 females. And if you take a look at how these females' weight is distributed, I hope that you can see that the distribution, it seems to fit this bell-shaped curve. And I know it doesn't fit it perfectly, but it kind of follows that shape where we see we have the highest frequencies close to the center of the curve. And then as we move away from the center, we see that we have some females who weigh more than, so what would you say at the center? What is that? Approximately, oops, let me use a different color pen here. That looks like it's approximately 75 kilograms. Okay, so most women weigh around 75 kilograms, with fewer women weighing much more, and then fewer women weighing much less. So as we move to the left of the center, we see that we do have women who weigh less than 75 kilograms, but that frequency occurs less often. Okay, so what does it mean when we say that our distribution has this bell-shaped curve? Bell-shaped curve distributions have a specific name. We call them a normal distribution. So a normal distribution is a probability distribution. I'll grab my pen. It's a probability distribution that is symmetrical around the mean. So that is symmetrical. And anytime that you have a normal distribution, that mean is always going to be at the center of your distribution. Okay. All right, so again, if we take a look at this, it turns out that the sample mean is actually that green line. So this green line here, that's the sample mean, and it's actually 77.6 kilograms. So if I were to summarize the weight of females, I can say that the distribution for the weight of females appears approximately normal, where the typical weight of a female is around 77.6 kilograms. And we have some females who weigh more and some females who weigh less than that mean amount. But we can also see at the center of the distribution here, this red line, this represents the sample median. And the sample median for this set is actually 74 kilograms, 74 kilograms. So anytime that you have data that's normally distributed and you want to summarize and talk about what the typical weight of a female is or whatever your data set is about, you can use either the mean or the median to describe or summarize your data because they are very close in value. So hopefully you can see that 74 kilograms and 77.6 kilograms are pretty close to each other, okay? And later on, we'll take a look at the math behind this, but I hope that you can see that it would make sense that if we're looking at the sample mean, where the sample mean represents an average, so if the mean is a type of average, then if we take all of our values, you take your low values and your high values and you average it together, you're going to end up in the center. So that's why the mean and the median is considered a measure of center. Now on the right-hand side here, I've got a histogram also looking at weights, but now we've combined both male and female weights. And I want you to notice also that our sample size increased from 147 to now 300. So it turns out that as your sample gets larger and larger, the distribution of your data is going to appear more bell-shaped. So if I were to compare the histogram on the right with the histogram on the left, I hope that you can see that on the right, that distribution fits that bell curve a little bit better than the histogram on the left. So this tells us that the majority of adults here, male and female, have weights that are close to. So if I were to calculate the mean and the median again, let me pull up my pen here. So the mean, sample mean here, is actually closer to 81.66 kilograms. And then the median, which is the left there, the red line, is 80.5 kilogram. So we see that the median and the sample mean get even closer to each other as our distribution becomes more bell-shaped and more approximately normal. And another thing that we can say when we're comparing these two histograms is that we can see that the histogram on the right seems a little bit more compact, meaning that we have more values. So we have more values that are closer to the center, whereas the distribution on the left, we can see that there is a little bit more variation. So the variation in weights is less when our sample size is a little bit larger. And also the distribution appears more normally distributed as our sample size gets larger. So what happens when your data does not have a normal distribution, but it's skewed? So here I have an example of a distribution that represents the income for people who live in New York, and it's measured in thousands of dollars. So hopefully you can see here that the distribution, it does not look bell-shaped. In fact, it's skewed to the right. So data that's skewed to the right is data where you have high frequency bars on the low end of the distribution, and then you have fewer frequency bars far out to the right. So we said that this is an example of data that has a distribution that is right skewed. So right skewed distribution. And if you want to know what a left skewed distribution is, it's going to be the opposite. So left skewed distribution is when you have low frequency bars on the left and then higher frequency bars as you move to the right. So this is an example of a left skewed distribution. Okay, so what about summarizing this data? If I want to describe or summarize in general, right, what the typical income is for a New Yorker, using the mean, so here this represents the sample mean, using the mean of 27,200 would not be representative of a typical person in New York because we've got some values here, a few outliers that are very, very far away. So hopefully you can see that it's very far away from the majority of New Yorkers' income. And that that outlier is going to pull the mean up. Okay, so it's going to make that mean value a lot higher, and so that's not representative of most people's income in New York. So instead of using the mean whenever you have data that is skewed, a better measure of center to use to describe the typical value for your distribution is to use the median. So here we can see that if we calculate the median, right, the median is going to be closer to where we see the majority of the frequency bars because that's how we break up the data. And the median value here is actually closer to 15,800, clearly more representative of what's going on with the majority of people's income in New York. Let's take a look at an example and I'll show you how to calculate the mean, and we'll also calculate the median. We'll do it by hand, and then in the next video, I'll show you how to use your graphing calculator and have your calculator find these statistics for you. So to calculate our sample mean here, I've collected the height of 7 people in one of our statistics class. So you can see here that their heights are listed on the right. And so to calculate the mean, I need to sum up all of those values and divide by the sample size. So here, if I take 60 plus 62 plus 68 plus 70 plus 64 plus 72 plus 61 and divide that by 7, I end up with 457 divided by 7, which gives us a sample mean of 65.29 inches. Okay, all right, let's go ahead and calculate the median. So the median, first thing that I have to do is put my data in order from least to greatest. So let's do 60, 61, 62, 64, 68, and 70 and 72. And because this is an odd data set, we can find the median exactly in the center. So our median is 64 inches. Okay. All right, so if I had to describe the typical height of these 7 people, you can say that the typical height is around 65 inches or 64 inches, and either one of those statistics will be a good measure of center for this relatively small data set. Now let's talk about what's going to happen to the mean if we were to add a famous basketball player. So let's say we add, I don't know if you guys know Yao Ming. He's not as popular as your LeBron James or Kobe Bryant or Shaquille O'Neal, but he is 90 inches tall. So if I were to add this outlier to my data set, what do you think is going to happen to my sample mean? Well, it's going to take the sample mean and it's going to pull it up. So we had an original sum of the 7 students' height as 457. So now let's add Yao Ming, add 90, and our sample size is now going to increase by just one more person, so 7 to 8. Right, but because that's an outlier, it's going to pull the sample mean up. And so here we end up getting 68.38 inches, which is approximately 5 feet 8 inches. Okay, now let's see what happens to the median. So adding an outlier, how does that affect the median? So hopefully you can see here that the median does not get affected as much by an outlier versus the mean. So here if I try to find the middle value, because I have an even data set now to calculate the median, I have to figure out what's exactly between 64 and 68. So if we add them and divide by 2, that gives us a median value of 66 inches. Okay. All right, so you can see here that increasing the mean from 65 to 68 is much more significant than increasing the mean from 64 to 66 inches. So the mean gets affected by outliers, whether that outlier is a very, very large number or a very, very small number.